Hello and welcome to another power system analysis class. In the previous class, we started ideal transformers, saw some problems. We didn't have any classes last week because of the breaks, and before that we had the exam. So ideal transformers. In ideal transformers, we had an assumption. We assumed that we have no losses, no core losses, no wire, resistance. So it's an ideal situation. And for an ideal transformer, we reached a very simple equation. The primary voltage to the secondary voltage is going to be N1 over N2, or in other words, V1 over N1 is equal to V2 over N2. And A is called, which is N1 over N2. By the way, N1 is the primary turn, and the N2 is the secondary turn, and A would be our turn ratio. And with the same turn ratio that increases the voltage, we have a reduction in current because the input power is equal to the output power. We don't have any power loss. We don't generate any power in transformers. Therefore, I1 over I2 is going to be N2 over N1. In other words, I1 over I2 is going to be N2 over N1, or N1 over A, which is our turn ratio. And we solved some practice problems as well. When we add the matrices for V and I, we reached the impedance on the primary side. And if we want to find the impedance on the primary side, we would multiply the impedance on the load or the secondary side. Usually the load is the secondary side and the primary is the generator. We just multiply that by A squared, which is the turn ratio on a power of 2. And we solved some practice problems on this as well. Today we will continue with the real transformers. I already started this. I just wanted to do a quick review on ideal transformers as well. And we will solve as many problems as we can, because this is a very important topic. You're going to see this in your labs as well. We're going to have a couple of labs in this class. And using these different tests, we can determine different parameters of real transformers. So real transformers, they have losses, they have leakage flux, and they have finite permeability of magnetic core. The real power losses are the power losses that we have from the resistance in the wires and winding, which is going to be I squared R. And core losses, which are magnetic losses due to eddy currents and hysteresis. We explained a little bit about hysteresis and eddy current as well. Eddy current arises because of the changing of flux in core. We can reduce eddy currents by laminating the core. And this is an example of how we do it. What you do technically is, instead of having one single block of core, we just put different sheets, and we don't have to actually insulate them. What we can do usually, we just glue them together. And then so we have sheets of steel that are attached to each other. Sometimes we just, screw them. We put a screw from each end. And that causes the eddy current to reduce. And the other thing is hysteresis losses, and these are proportional to the area of BH core curve and the frequency. Hysteresis losses are due to the physical properties of the core and the material that the core is made out of. Using different alloys, we can reduce this hysteresis, and technically hysteresis is the residual magnetic field that is left in the core. One example that I gave you is, imagine when you have a nail and you put a wire around it and you run a current through that wire, you're magnetizing that nail, and now this nail becomes a magnet. If you cut the current through the wire, the nail would keep its magnetic field for a while. And depending on what alloy you're using, you could have a very powerful magnet or a magnet like if you have a aluminum or something like that, it's gonna quickly fade off. So it depends on the alloy that we are using. So we can't change it with changing the shape like we did in eddy current. We have to use a different alloy. We have to use something that has a BH curve that looks like the right one, so we don't have a lot of residual. So by changing the material and using material with a thin BH curve, we can reduce the hysteresis losses. And what happens here is I have to use my pen. Is I'm going to give you a quick example. Is imagine the example that I gave you that we have a nail, and on that nail we have a wire, around that nail. And if I put the current this way, then according to the right-hand law, you're going to have a magnetic field that is going from right to left. Okay. Now, if I have an alternating current and at the next cycle, the current is going in the opposite direction, I'm going to have a magnetic field that is going in the opposite direction. But the problem is the first magnetic field, if you have hysteresis, has caused a little magnetic inside the core, which is the nail. And when you have the second one, it's going to be in an opposite direction and contradict the first one. Therefore, you're going to have a smaller magnetic field. Okay, so hysteresis, and this causes a loss. This causes loss in the system. So different type of material will reduce this hysteresis. Yes, please. Okay, perfect. So that's a great question. Now we use a specialized type of steel. But the thing is, we have very expensive alloys that we use in MRI machines that we don't. But the thing is, if you want to build that transformer that is 2 metric tons, I don't know if you've seen those transformers. Some of them are 5 tons, 6 tons, 10 tons, and the core itself is like 2 tons. You can't build it using that type of nickel alloy. They use rare earth materials like vanadium and so on. If you want to build like a better one, the thing is those are extremely expensive, and they are just reserved for high-end devices like MRIs. And transformers, we want to make them good, but at the same time, we want to make them cheap. So we don't have that luxury of having those rare earth materials inside. But the majority of the metal inside is steel. It's not even stainless steel. It's type of steel, carbon steel, but with different type of alloys in them. Like usually they have nickel and vanadium and so on. But again, changing a little bit that alloy is going to change that hysteresis, but it comes with a cost. But thing that I've seen in my experience, usually when a transformer is at its end of life cycle, and they rip it apart, the only part they are interested in is the copper. They don't even care about the core. But that's usually the cheapest parts of that. So it's the regular steel that they melt and build again. So they don't make it out of high-end alloy materials. The copper is like 20, 30 times more expensive than the core itself. The core is the cheap part. Now, in these magnetic field, we also have leakage, as mentioned, because not all the magnetic flux goes through the core. So in that case, we can find the leakage, the effects of leakage. Not all flux is within the transformer core. So again, if I have a transformer core, we're gonna have some magnetic flux which is out of the core itself, and not all of them goes as the flux inside the core. So some of these are gonna be wasted or leakage. And we can find it using this equation. Delta 1 is going to be equal to delta 1 L1 plus N1 phi M. Sometimes we should with delta shown, sometimes we show with the llama, by the way. Delta 2 is delta L2 plus N2 phi M. So from this primary winding and from the secondary winding, assuming a linear magnetic medium, we get L1. It's going to be equal to L1, L1, I1, L2, I'm sorry, delta L2 is going to be L2, I prime 2. And with that, we can find V1 and V2, which V1 is going to be R1 I1 plus L1 dI1 over dt plus N1 d phi m over dt. And V2 is going to be from the secondary side. Now, the effects of finite core permeability. This means that we have non-zero MMF, which is required to maintain phi m in the core. Therefore, N1 I1 minus N2 I2 is going to be rho phi m. This value is usually modeled as magnetizing core, which is going to be I1 is going to be equal to rho phi m over N1 plus N2 over N1 I2. And therefore, I1 would be equal to Im plus N2 over N1 I2, where Im is rho phi m over N1. Now, using the previous relationship, we can derive an equivalent circuit model for the real transformer, which looks like this. So in the real transformer, we didn't have the primary resistance, we didn't have the leakage, we don't have the permeability problem, but now we have all of them. And you can see that we model the input resistance of the wiring with R1, and then we have JX1, XM, RC, which is our leakage, our permeability, and our reluctance in the system, and also the core resistance. And at the same time, we have the same thing, the leakage and also the resistance and the secondary part. Now, this model is further simplified by referring all impedances to the primary side. So what we get finally, and this is very important, you need to memorize this. This is a simplified equivalent circuit. We model all of them to the primary side. We have RE and JXE, which are our real resistance and our inductance, reluctance. And also we have the core loss, which we model it using this, which is RC parallel with JXM. And for simplifying it, we would assume we have a turn ratio of 8:1. Now, to calculate the losses in the transformer, we have different methods to do that. So imagine that someone gives you a transformer and asks for the leakage, for the reluctance, for resistance. How can you do that? So first of all, each transformer comes with a plate that gives you some parameters, but most of the time you have to determine the parameters of the transformer. And to determine those parameters, you need to do some non-destructive testing on that, okay? And we have two types of testing, which are very important. I'm going to show you how we do that in the lab as well, which are the open circuit test and the short circuit test. So the parameters are, the model are determined based upon First, the nameplate data gives the rated voltage and power, but it doesn't give you other parameters usually, like the resistance. Sometimes it does, but most times it doesn't. Like the internal resistance, the permeability, and other leakage, and how much insulation, because you don't know what's happening in a transformer. You just have a box, big box, black box, imagine, and you have an input and you have an output. That's it. And you don't know what's inside, what type of, insulation they are using, what size of copper wiring they are using. The only thing that is usually given, sometimes you don't even have that, is the turn ratio and the rated power and voltage, meaning how much maximum power and voltage that you can give before you blow the transformer. Sometimes most transformers that, if you buy a transformer from Alibaba or something, you don't even see those nameplates, nothing. It's just, a simple transformer, and you have no clue what's inside. Now, to determine the parameters of a non-ideal transformers, we do two tests on them. One is the open circuit test. And in this test, the OC test, open circuit test, a rated voltage is applied to the primary with secondary open. So, for example, we give it 220 or let's say 120 volts. We measure the primary current, this current, I, and what does this current give us? If we have an ideal transformer and we don't have any load, the current would be zero, perfect. But since this is a non-ideal, we have losses. And by measuring that current, and we already have the voltage that we have fixed and determined, you have to, and by the way, in the lab, what you do is you fix the voltage and you measure that voltage, and then you apply it to the transformer and you measure the current, and therefore you can determine the primary current losses. And the test may also be done applying the voltage to the secondary, calculating the values, then referring the values back to the primary side, as you know. But using this test, you can determine the losses that we have. And the second one is short circuit test. With secondary shorted, we apply the voltage to the primary to get rated current to flow, measure voltage and losses. Now the short circuit test is a little bit more tricky, and I've been doing this lab since 10 years ago. First experience that I had, and when I was doing that back then, I was a TA, and someone almost got killed because they applied a huge voltage to a short circuit and exploded the whole thing. The whole desk went black. So it's when you're applying it as a short circuit, you have to be very careful. You have to start with a zero voltage and slowly increase that. Because if you give it a rated voltage of 120, you're going to have a short circuit, and it's going to be it has the setting if it's going to damage capacity, but you're going to have maximum current passing through. And if you are connected to, you're not connected to a proper, breaker, it's going to draw a lot of current and it's going to blow up the whole thing. So for a short circuit, you start with a very low voltage, usually around 1-2 volts, sometimes a few volts. And then you measure the current passing through the secondary, and therefore, and the voltage and the current. And by that, you can determine the turn ratio, you can determine the current, and from that current, you can determine the losses, the core losses in the system as well. So the primary one, the open circuit, is usually to determine the resistor losses and so on. Second one is resistance and also core losses. And I'll give you some examples on how we do it. It's better to learn with an example. Now, the first example, and I'll show you how we determine the losses. We have a single phase 100 megavolt amp, 200 to 80 kilovolt transformer, which has the following test data. In open circuit, 20 amps pass with 10 kilowatt losses. In short circuit, we have 30 kilovolts with 500 kilowatt losses. We want to determine the model parameters. Now, first thing we do, we can draw the model, which we have RE, JXE, RC, and JXM. And the ratio, determine the ratio is N1 over N2, which is 200 over 80, which gives us 2.5. Okay. Which is over here as well. Now what we want to do is we want to find the current in short circuit. So in the current in the short circuit is I short circuit is S over V. Now what is S? S is 100 megavolt amp and V is 200 kilovolts, which gives us 500 amps. By the way, this is a huge transformer. So this much current doesn't, the transformers that we have are very small, and even a few more than like 30, 40 amps, it's going to destroy the transformer. So it depends on the transformer. This is a 100 megavolt amp transformer. This transformer could supply the whole city, like half the city of, yeah, half of Amarillo. Okay. Now the second part, we want to find S. What is S equal to? P plus JQ. In other words, if we want to find Z, Z is what? R plus JXE. So the impedance here, this is Z, is equal to R plus JXE, which is equal to what? What is Z according to the Ohm's law? V over I, yes? Now, how much is our voltage? No, for the short circuit, 30 kilovolts. And how much is our current? 500 amps, okay? So when you want to find the short circuit current, you divide that from the nominal voltage, which was 200, for the primary, and then you get that short circuit current. Now, 30 kilovolts divided by 500 amps gives you 60 ohms. Now, P of the short circuit was already given at 500 kilowatt losses. So using the equation Ri squared is going to be 500 kilowatts. We already know that I is equal to 500. So 500 in the power of 2 is going to give us what? 25,000. Sorry, 250,000. And therefore RE would give us 2 ohms. Which you can see for a transformer this size, it's very small resistor. This is this transformer is the size of this class, even bigger. So hence, using this equation, we can find XE. Now, if we want to find the magnitude of XE, Z squared is going to be R squared plus XE squared. In other words, XE is going to be square root of Z squared minus RE squared. So we apply it in this equation, which is going to be Z, which is our impedance. We found it at 60 and R is at 2. So if we round it up, it's going to be close to the 60 ohms, very close to that. Not 6, like 59 point something ohms. Now from the open circuit test, RC is going to be equal to 200 kilovolts square over 10 kilowatts. How did we get this equation? The power loss was 10 kilowatts. What is the equation for power? V squared over RC. Yes. Now, 10 kilowatt would be V square, which is 200 kilovolt, or 200,000 square over RC. And when we replace that, we get RC at 4 mega ohms. Now, to find the resistance, we have to add all these resistances together to find the core resistance. So RE plus JXE plus JXM, so JXE and plus JXM gives us the RC, which is 200 kilovolts over 20 amps. I'm sorry, which gives us the total core resistance, which is going to be 10,000 ohms. In other words, XM of the core is going to be 10,000. It's going to be 10,000 ohms. Okay. Now let's solve another example. Now in this example, we have an open circuit test example. Given a one-phase transformer assisted from the low voltage side, the rated applied voltage is 240 volts. The open circuit current is 2.5 amps. The open circuit power is 120 watts. And we want to find RC and XM referred to the test side. Okay. So again, we have a transformer. We don't know what is inside that. The only thing that we know is that we have done an open circuit test on it. And from that, the rated applied voltage for the open circuit means we have left the secondary open, and we have given a voltage of 200, and we have a voltage of 240 volts. The open circuit current is 2.5 amps at 240 volts. And the power of the open circuit is 120 watts. We want to find RC and XM. So in the previous one, we had the losses, and we had the current, and we had S. Here, we have the open circuit power, we have the open circuit current, and we have the rated voltage applied, where we don't have the nominal power. Okay. Now, the first thing that I want to find is I want to find the power. And by the way, I'm going to use another way to solve it using the power factor. Cosine of phi, do you remember what cosine of phi was? The equation for it? So do you remember the power triangle? This is S, this is P. This is what? Q. What is cosine of phi? Perfect, P over S. And we already have P and we can find S. S is equal to the OC over IOC. So S would be 240 times 2.5 amp, which gives us 600. Now we can find cosine of phi as 120 over VOC IOC, which gives us 120 divided by 600, gives us 0.2. Now phi would be cosine inverse of 0.2. Can someone find this for me? 46 degrees. Give me a second. I want to put my tablet on low power mode so we won't run out of power. And next thing we do, we want to draw. Can copy it. I think it's going to be better to copy this. The core model here. So the current that we have, IC, is actually split into the core losses that we have here, which are core losses. Let me do it in this page. So the IC that we have is split between the core losses. IC is the current is split into core losses and for magnetizing components. Therefore, IC would be I of open circuit times cosine of phi, which gives us 2.5 times 0.2, which is 0.5 amps. Now, I for the magnetizing part is I of open circuit sine of phi. And since sine of phi, this is another way to solve it. You can always solve it using the previous method as well. Minus cosine of phi, which is 0.2 and a power of 2. This gives us 0.96, and the square root is 0.978. Therefore, IM would be equal to 2.5, which is I of our open circuit, times sine of phi, which is 0.978, 979, gives us 2.45 amps. which you can see it's the same that we had. We have a small loss in the system from 2.45 to 2.45. It's a very, very small loss magnetizing in the system. Now, RC is VOC over IC as we had previously, which is going to be 240 divided by IC, which is 0.5, gives us 480 ohms. And XM would be VOC over IM, which is going to be 240 divided by 2.45, which gives us 97.98 ohms. So there are two ways to solve the problem. One is you can use Z square is going to be equal to R square plus XE square, or in other words, Z is going to be R plus JXE. And where do you find Z? It's going to be V over I. And you can, if you have R, you can get this and you're going to get the same results. Or I can use the angular form, and I can use, instead of finding R, I can find cosine of phi, which is the angle. And from that, I can find Z and I can find Q as well, or XE as well. So two different ways to solve this. Now, therefore, RC would be 480 ohms and XM would be around 98 ohms.